Okay, so what we're going to be talking about today is something called a normal approximation to the binomial. You might remember in the past we talked about binomial distributions, which is a discrete probability distribution that lets you determine the probability of certain types of countable events. Okay, by discrete, I mean the outcomes are countable, such as the number of heads you might get if you flipped a fair coin 50 times. Okay, if you might remember, some of the criteria for using binomial are you do the same experiment over and over again. Okay, they're called trials. And the probability of a success, like say getting ahead, doesn't change from one trial to the next. Also, the trials are independent. The outcome of one isn't going to influence the next trial. Okay, so as long as, and oh yeah, you can only have a success or a failure, all right? So we might say getting heads is a success. Somebody else might say getting tails is a success. Doesn't matter, okay? It's however you define success and failure. So again, those are called binomial experiments. Now you might remember the last time we were together, we talked about the normal distribution. That's a continuous probability distribution, and it's used for measurable outcomes, like shoe sizes or heights in a population. Okay, there's a very powerful result that was developed in the early 1800s by a mathematician named Laplace that said, you know, for samples that are big enough, you can kind of approximate just about any distribution, even if it's not normal, by the normal distribution. Okay, this turns out to be a really, really useful result in probability and statistics, especially when you're dealing with unknown probability distributions. Okay, so we're going to be talking about using the normal distribution, which is continuous, to approximate the discrete binomial distribution. Just realize this result holds in general as long as you've got large sample sizes. Okay, so let me share my screen with you. And I'm going to start out by using my notes, and I'm going to periodically switch over to either a Word document where we can work or the TI-84, whatever is useful at the time. Okay, and as always, if you've got a question, type it in the chat, and I'd be happy to, stop from time to time and review any questions that are in the chat. Okay, so as I mentioned, if I run a binomial experiment with a really large number of trials, I can kind of model the probabilities that come out of binomial with normal probabilities. Now, they're not going to be exact. It's called an approximation for a reason. Okay, and although this result is like more than 150 years old, you have to understand that it has most of its uses in statistics today with modeling unknown probability distributions by the normal. In other words, if I take a big enough sample, maybe I can use the normal to handle this. Okay. Using it to model the binomial is kind of not really necessary anymore because of advances in computing. If you read your textbook, which is about 10 years old, it'll say things like, oh, well, a calculator can't handle a very big sample size. That may be true about the TI-84, but we have apps today that can certainly handle very, very large sample sizes. So the argument that we need to approximate the binomial because we can't run the binomial distribution with really large exponents, that's not true anymore. Okay, so full disclosure, want to be transparent. Okay, again, the result is mainly useful for other types of distributions where you're not sure what you have. Okay, so let me show you how this works. Okay, here's a hypothetical situation. Let's say we have a study that reports about 40% of Atlanta drivers exceed the speed limit by at least 20 miles an hour. Yikes, okay? So exceeding the speed limit by 20 or more in most places is called criminal speeding, okay? That gets you a really hefty fine, can even get you points on your license, okay? So suppose a state trooper records the speed of a random sample of 10 drivers and finds that 50% of them, 5 out of 10, exceed the speed limit by 20 miles an hour. How likely is this if the 40% figure is accurate? In other words, he found a higher percentage, okay? You can answer this with a binomial probability distribution, okay? Because again, he's picking people, randomly out of the population, okay, and recording their speed, probably with a radar gun, right? So he's doing the same experiment 10 times. We're assuming the people on the road are somewhat independent, particularly if he leaves enough space between the people he picks, right? And we're assuming that getting someone who speeds by more than 20 miles an hour is called a success, okay? So again, binomial would work in this case. So we have to remember variables that go into binomial. Okay, you've got n, which is the total number of trials, that's 10 in our case. X is the number of successes, 5 successes, that's what he found, with a probability of 0.4. Namely, that's the random driver speeding more than 20 miles an hour. So here's the binomial formula. You might remember seeing that in the text, okay? And if I crank the formula, I get 0.2007. So there's a 20% chance of this happening if the 40% figure is normal. In other words, if that's our binomial probability, okay? Just so you're comfortable, I know I'm telling you, you don't have to crank the formula. Let's take a look at the TI-84 real quick, okay? And here's what I typed into the TI-84. I typed in binom PDF. Number of trials is 10. Okay, the probability of a success is 40%. And I'm looking for 5 successes. And you can see, rounded to the 4th decimal place, I got the same value, 0.2001. This would be a 7. Okay? So again, I just wanted to show you, you can do this on your calculator. You don't have to crank the formula. So the probability is 20%, which in binomial land is a reasonable probability, a super low one. Okay, so the result isn't terribly unusual. Okay, suppose the trooper decides to take a much larger sample of drivers, say 100. Okay, let's say we wanted to know the probability that at least 50%, that means 50 or more of these drivers, were speeding. If that 40% figure is accurate, here's what you would have to do. Okay, remember, if you're using binom CDF, you're using the cumulative probability distribution. Okay, what you're going to get is you're going to get from 0 up to that number. Okay, so again, if I want 50 or more, I want the right-hand side of the binomial distribution. I want 50, 51, 52, 53, all the way out to 100, okay? Binom CDF is going to give you the other side, okay? So what you want to do is you want to take the whole distribution's probability, which is 1, and you want to subtract the 0 through 49 case, okay? If you subtract 0 through 49 people speeding, you're going to get 50, 51, 52, 53, okay? So that's why I'm using 1 minus binom CDF, number of trials is 100, probability of success 0.4, and I'm looking for 0 to 49 successes. If I subtract that from 1, I'm going to get the 50, 51, 52 that I'm looking for. Let me stop and ask, does the binom CDF make sense? Okay, I want to make sure you understand the logic of what I'm doing here. Please just Pipe in with either a yes or a no, ask a question, okay? Again, this needs to make sense. That's more important, actually, than getting the right number. All right. So again, I get about a 2% chance, okay? That basically says, well, you know, that 50% or more we're speeding, okay? Remember, in this question, I asked for exactly 50%, okay? Here I'm saying 50% or more, okay? So again, this method fails, okay, as n gets larger, since eventually the will overflow. You'll get an error with binomial CDF, okay? Again, just for transparency, there are other binomial calculators that have no problem with really large values of n, okay? But let's introduce this method that, again, Laplace came up with as an approximation. Again, the idea behind this is, well, let's see if we have a big enough sample size, just about any is going to approximate the normal, okay? All right, so like I said before, like when we do binomial, there are some criteria you have to come up with first. You have to satisfy. And the same is true about using this approximation. So in other words, to use a normal approximation, both n times p, okay, and n times 1 minus p should be greater than 5, okay? So in other words, this prevents you from using the approximation when your probability is either really large, the probability of success is really large or really small. That's where the approximation breaks down, okay? So let's take a look. You're also going to need to calculate the mean and the standard deviation of your binomial distribution. We haven't talked about this before, so I'll share it with you now, okay? The population mean of a binomial distribution is given by the number of trials times the probability of success, okay? If you think of it, it kind of makes sense, right? Think about it in terms of coin flipping, right? If I flip a fair coin 100 times, the probability of getting heads is 1/2, okay? I would expect on average 100 times a half, or 50 heads, right? That would be my expected value. So that makes sense, okay? The standard deviation is a little less transparent to see, but here's the way you would calculate the population standard deviation for a binomial distribution, okay? And remember, I'm using the Greek letters, so I'm talking about population here. It's the square root of number of trials times the probability of success, these two are given to you usually, times the probability of failure, okay? Think about it this way. If the probability of success is 0.4, then the probability of failure is 1 minus 0.4, or 0.6, okay? So that's what 1 minus p is. It's the probability of not a success, okay? So you need these two in order to be able to use this normal approximation. Because if you think about it, when you use normal CDF, one of the things that asks you for is the mean and the standard deviation of your population. Okay, so you have to compute those in advance. Please also understand that in your book, they make you compute z-scores for these, and they make you use a normal table. You don't need to do that. You can use normal CDF, okay? If anybody wants to learn how to use the normal table really well, I'll be happy to explain it to you. But again, we have things that are a little bit more up to date here. Okay, so let's say we have our binomial distribution with a number of cars that are speeding, right? And our number of trials, the trooper got speeds for 100 cars, so n is 100. We're assuming the probability that somebody's speeding more than 20 miles an hour is 0.4. Let's calculate the mean and the standard deviation of of this distribution, okay? So the mean, okay, or the expected value is kind of 100 times 0.4. We'd expect about 40 people to be speeding 20 miles an hour or more over the limit, right? That's what this is telling us. The standard deviation, and again, you can calculate this on your calculator, square root of number of trials times probability of success times probability of failure. These two must, in a binomial distribution, they must add up to 1. Remember, because there's only 2 outcomes, success or failure. So multiplying all this together and taking the square root, we get 4.899. Okay, so now we have a mean and a standard deviation. Now the problem with approximating binomial by a normal distribution is binomial is a discrete probability distribution, and the normal distribution is continuous. Okay, let me show you a picture that's in our math, my math lab course. It's in our notes and videos section. So let me go there. And hopefully I'll be able to bring this up on the screen. Okay, this is in our videos and notes and videos section, and it's right in there. It's called continuity correction. Okay, and what that's telling you is, well, I'm trying to use something continuous, that's this smooth curve, to approximate something that's discrete. That's the chunky curve. Okay, you can see, if you look at the diagram, that the chunks of binomial hang outside your curve at various points. Okay, so what you're going to need to do is you're going to need to adjust your x value to compensate for that. Okay, and that's called a continuity correction factor. So in order to use this normal approximation, the first thing we did was to compute the mean and standard deviation of the binomial distribution we're trying to approximate. The next thing we're going to have to do is we're going to have to mess with our x values a little according to this continuity correction factor to account for the fact we're putting a smooth curve on top of a chunky one. Okay? And again, I kind of mention here again, this theorem, I say a very famous theorem by Laplace, it's called the Central Limit Theorem, and it's kind of the backbone of modern statistics and probability, okay? And it says, if you take enough really large samples, the sample mean from your distribution is going to approximate the normal eventually, okay? And that's what we're using here, okay? So here's the adjustment that we're going to make. This continuity correction factor in determining the normal probabilities, okay? And again, we're doing this because we're taking something smooth and putting it on top of something that's not smooth, okay? The binomial has discrete chunks, okay? So this part is not in your text anywhere. The only place this exists is in your notes and in the course notes and videos section of my math lab, okay? So it's really, really important that you know where to find this, because personally, I find the way your book does it extremely confusing, okay? So what this means is, if you're starting out with a probability that x actually equals a number, like for example, x is 5, okay? You're going to have to find the normal, this is binomial on the left, the normal probabilities are going to be here on the right. So you're going to have to take your n value, say like 5, subtract 1/2 from it. So this would be 4.5, and then add 0.5 to it and put it on the other side. So if your binomial probability says you want the probability that x is exactly 5, the normal says you're going to have to find the probability that x is between 4.5 and 5.5. Again, we're trying to get that smooth curve to fit over the chunky one. Okay, if your binomial probability says x is greater than 5, your normal probability says x is greater than 5.5. Okay, if the binomial probability says x is less than or equal to 5, the normal probability says x is less than 5.5. Okay, Does everybody see how I'm doing this? Okay, does everybody see how I'm using the continuity correction? Again, these are the binomial X values. All right, here are the normal ones, the ones you're going to adjust a little. Okay? Right, and this is really what you need. Again, I can't convey it to you enough. This exists here in the notes, and I'll shoot back hopefully to our course and show it to you again. Here it is in our course. Okay, continuity correction factor. Okay, so again, please find that in one of these two places, either in my notes or in the notes and videos section of the course. You're going to need to refer to it. It's not in your text anywhere. All right, well, let's use it in an example. Here's how you would apply it, okay? So I want to approximate the binomial situation of the state trooper, checking the speeds of 100 people, okay? So I want to find the probability that at least 50 out of 100 of the sample drivers exceed the speed limit, okay? So first I have to check that n times p and n times 1 minus p are both greater than 5, okay? With a probability of 0.4, I'm probably good, okay? Because again, remember, this test is meant to avoid using the approximation when your p is really close to 1 or really close to 0, okay? But let's just do the check anyway so you can see how it works. Here I have 100 times 0.4, that's 40, that's greater than 5. Here I have n times 1 minus p, so that's 100 times 0.6, that's 60. They're both greater than 5. That means I can use normal approximation safely. Okay, so let me just go down here. We already determined the mean and the standard deviation of this binomial distribution, okay? Just to refer back to that, I'll show you where that is up here. Notes. Okay, mean is n times p, standard deviation, and these are both for the population, square root of n times p times 1 minus p. Okay, so basically we have a question about what n and x stand for. In a binomial distribution, n is the number of trials. Okay, so how many times you're going to repeat the experiment. P is the probability of success on any given trial. In our example, that's 0.4. Okay, and x is the total number of successes you want to find. Okay, so in my example here, my total number, it's not going to affect and mu or a sigma. Okay, notice there's no x in here. Okay, but further down in my example, okay, I'm interested in finding 50 out of 100. So in this example, 100 is my n and 50 is my x. Okay, is that clearer as far as what the different variables mean? Okay, remember, n and p and x don't come into play with normal so much. I mean, x is going to translate into your upper and lower limits on normal CDF, okay? But as variables, that's a binomial thing. It's not a normal thing. And again, what we need to do, okay, we've got our n and we've got our mean and our standard deviation already here, okay? And I'm saying I want to know the probability that at least 50, what does at least 50 mean? It means 50 or more. So my x value is x is greater than or equal to 50. All right, so this is a translation from English into math, right? You have to remember that at least means greater than or equal to. Right? So this is my binomial x, okay? I want x greater than or equal to 50, and I have to use the continuity correction factor for greater than or equal to. Going back up here, you can see it's the last one, okay? If x is greater than or equal to some number, I'm going to use, okay, the probability that x is greater than that number minus 0.5, okay? And again, don't ask why this is. It basically is because you're trying to fit that smooth curve onto the bumpy curve, okay? The values are what they are in order to make that work, okay? So instead of 50, I'm going to have 50 minus 0.5, okay? Or I want the probability that x is greater than 49.5. Does everybody understand how I used the continuity correction factor? Okay, it's important to understand where 49.5 came from. Okay. Anybody else have a question about it? Okay, again, it's important to make sure you knew where it came from. Again, it's from that continuity correction factor table. Anybody have questions about where I got this from? Are we good? Now, as I said, your book has you do a real old school thing, and it has you calculate the z-score for this value, then look up the probability in a normal table. Okay, remember, you use z-scores for two things, okay? You use z-scores if you need to use a normal table, because the normal table is based on a standard normal distribution with a mean of 0 and a standard deviation of 1. So finding a z-score standardizes your values, okay? We don't need to do that anymore, okay? We have better technology. The other reason for using z-scores, and I brought this up at the end of our last session, is to compare scores within two different distributions, okay? So basically, if you remember our friend Alex, who had a vocabulary score of 66 and a math score of 75, and we wanted to know which one was better. In order to do that, we had to compare the z-scores of those two because they came from different distributions. That's still a valid use, okay? Anyway, I'm not going to use z-scores here because I have better technology. I'm going to use normal CDF, okay? Now think about it. We want to know, okay, if you look at our probability here, the probability that we get more than 49.5 speeders, okay? Whatever that means, okay? So 49.5 is our adjusted 50 value. That's the lowest value that we expect to find. That means on our upper value needs to be infinity, okay? Remember how the normal curve has a low and a high, okay? So greater than means greater than without a bound, okay? So our upper bound's infinity, okay? We calculated the mean of our distribution to be 40 and the standard deviation to be 4.899, okay? So here's where I'm actually using the normal approximation, okay? This is my adjusted x based on my continuity correction factor. Here is the mean of the binomial distribution this is coming from, and the standard deviation of the binomial it's coming from, okay? Is this normal CDF okay? Okay, does the normal CDF I have here make sense? Okay, again, the trick is to know where all of the pieces are coming from. Okay, you can use technology as long as you can build the input to it correctly. Okay. Again, this is going to return a value of approximately 0.0262, which is really close. If you remember, we were able to compute the actual binomial value of this because our n isn't that big yet. Okay, here's the value we got with our binomial, 0.0271. You can see these are really, really close. Okay, so again, this is a reasonable approximation. Okay, so let me ask any questions at this point on the process. Any questions on the process at this point? Okay, good. Everything else is pretty much a riff on the same idea. Okay, I'm going to show you one more example in the notes, and then we're going to do a couple ourselves. Okay, so you can get practice with actually working these out yourself. Okay, so here's the second example. Suppose we wanted the probability of finding between 42 and 48 speeders in that random sample of 100. So now we're asking for a slightly different outcome rather than more than 50 or at least 50. We want to know what's the probability that in a sample of 100 the trooper is going to find between 42 and 48 speeders. Okay, remember we have the same n and p values. Okay, so we know already that we can use the normal approximation that np is greater than 5 and n times 1 minus p is greater than 5. I haven't changed those, so I don't need to recompute that. I also don't need to recompute the mean and the standard deviation of the population because that hasn't changed, right? So I still have, I think, 40 and I forget what that was. 4.899. Okay. What I do have to change is the continuity correction factor. Okay. Because here is my binomial probability. I'm looking for the probability that my number of successes is between 42 and 48, including those endpoints. Okay. So if you want to look at it that way, you basically have to say that that's like having x is greater than 42. That's this part of the compound inequality. If you go up to continuity correction factor, okay, greater than or equal to says use greater than minus a half. So that's what I'm doing here. So this low end of this compound inequality says that x is greater than 41 and a half. Okay. How about the x is less than 48? Again, if I slide up to the continuity correction factor table, okay, you can see less than or equal says use less than plus a half. This line right here. So I'm going to add a half to the 48. And that becomes 48 and a half. Okay, now, basically, if you think about it, okay, saying x is greater than 41 and a half means 41 and a half is your low bound in normal CDF. Saying that x is less than 48 and a half says that 48 and a half is your upper bound in normal CDF. Okay? So here's what you're looking at. This is your new probability statement. Okay, x is between 41 and a half and 48 and a half. Okay, but that means 41 and a half is your low bound, 48 and a half is your high bound. Your mean and your standard deviation have unchanged, right? Haven't changed. So this gives you a 33.8% chance of finding, okay, speeders between 42 and 48 speeders in your sample. That's a pretty decent probability, okay? But you'd expect that given the fact that your probability is 0.4, right? So let me ask you at this point, does this example make sense? I am just showing you a different continuity correction factor because now we had a range of x's. Okay. I want to get a couple of yeses before we move on to some examples. Anybody have any questions at this point? And don't worry, if I have you do an example, I'll put up that continuity correction table. As always, in these types of situations, what's the most important is being able to translate from a real world situation, okay, into math. Make sure you check the assumptions of whatever model you decide to use. Then you can use technology to crank the model, okay? But that initial step of understanding what you're being asked for, right, and choosing the right model, that's something we can't offload onto technology. Not yet, anyway. Okay, so I'm going to close the notes and bring up a Word document. Okay, this is kind of our notes for today, and I'll just briefly go over it. I'm talking about the normal approximation to the binomial, and I'm saying it's useful when you have large sample sizes. It's also useful for unknown distributions, okay, and modeling them with the normal. This correction factor is needed because your normal distribution is continuous with measurable outcomes, and the binomial distribution is discrete with countable outcomes. So you're trying to fit something smooth to something that's not smooth. Before you use the approximation, you need to check that these binomial values, n times p and n times 1 minus p, are both greater than 5, okay? Again, this ensures your probability p isn't too close to 0 or 1. And you also need to calculate the mean, okay? U is n times p, and the standard deviation, sigma, is the square root of n times p times 1 minus p of the binomial that you're starting with, okay? Here's the continuity correction factor table, right? So here is what I would like you to try. Okay, hopefully everybody can see it. Okay. 2% of quartz heaters produced in a certain plant are defective. So, and you know this from historical data. Suppose the plant produced 10,000 such heaters last month. Find the probability using the normal approximation to the binomial that among these heaters you had fewer than 170 defective, more than 222 defective. Okay? So we're going to take some time to do this, and I'm going to work with you, okay? I'm going to try to leave this up here for you to see, okay? First thing you need to do is check the assumptions for using the approximation, okay? And then you need to compute mu and sigma, okay? Do that part first, okay? And then once you get this result, okay, for the criteria, say the criteria are okay in the chat. And then once you get mu and sigma, you can say mu is, sigma is, and you can spell out the words mu and sigma, okay? Everybody understand what I want you to do first, okay? All right, so first, check assumptions. Then find mu and sigma. Okay, do that first. All right, and I'll work along with you. All right, I'll put our answers in this sheet so you'll have them later. I know you're all probably still working, but if you take a look at what I have on the screen, you might be able to follow along to make sure you're checking correctly. So just take a look at what I have up here. I'll highlight my mu and my sigma so you can see those. How about the rest of you? Getting Again, it's kind of difficult to show everything all at once, but I've got the formulas from mu, sigma down here. I kind of need some feedback from you. Are you getting these or are you stuck somewhere? Okay, we've got two that are okay, good. Awesome. Awesome, very good. Okay, so now we are in a position to actually figure out what we have to do with our X value, okay? Basically, we want to know, we want the probability that what? That X is less than 170. So X less than 170, okay? That's binomial, okay? So I have to go up to my continuity correction table and see, okay, that's this one, right? X is less than some number. That means I have to change it to be less than that number minus 0.5. Okay, so adjust it to be the probability of X less than 170 minus 0.5, which is probability of X less than 169. Okay. Everybody okay with that much? Anybody have a problem with the adjustment? Adjustment to X, okay? This is the crucial part, guys. This is the part that makes it work, okay? Is adjusting your X value. Awesome. Okay. So here's our X value. I'm going to highlight that. X is less than that. Now, if X is less than that, how far to the left can I go? Okay. The high value is 169.5. So what's low value? What do you think? What should I put in for my low value? Is there a low value? If you say X can be less than 169.5. Well, theoretically, 0 is a low value here. But remember, you're talking about a normal curve and the tails go out forever. Okay. So if you go as far left as you can go, what are you heading towards? What should I use as the low value, guys? Remember on the normal, if there is no low value, you need to put in negative infinity. Okay, that's the model. Okay, the tails of the normal curve don't ever touch the x-axis. They go out forever. They approach it like an asymptote. Okay, so technically, those tails go out towards positive infinity and negative infinity. Okay, so here is what you're going to type into your calculator. Type in normal CDF. Okay, first I have to put in my low value. Make sure I have it spelled correctly. Normal CDF. Remember, we use that 1 and then the exponential that's over comma. Okay, so it's second comma. And it has to be negative because it's a lower bound. So leading negative sign. That's how we say negative infinity to the calculator. That's our low value. Here's our high value. Okay, the mean of the distribution is 200 and the standard deviation is 14. Okay, so type that in. Okay, I'll let you try it first. Try it yourself. And then we'll bring it up on the TI-84. Okay. Okay, I'm seeing a couple of values that are coming up to be 0.01468, okay, which says there's about a 1.5% chance, okay, that you'd get fewer than 170 defects. Okay. All right, so I'm going to put this here, and then I'm just going to briefly go over to show you that on the calculator to make sure everybody can get there. So here's my TI. And again, I'm going to go over to okay, so we're going to go to second theirs. That's our distributions. Normal CDF. Okay, lower already has this typed in. So let me show you how you do that. Leading negative, 1. And here's the double E that I was talking about. It's a shift on your comma key. So second, comma. It only puts one E in there. And what this is scientific notation. Essentially, negative 1e to the 99th is a negative 1 followed by 99 zeros. So a really massively negative number. Okay. Our upper bound was 169.5. That was our adjusted X value. Our mean that we calculated was 200, and our standard deviation was 14. I paste it and I run it. I get the same value everybody else is getting. Okay. So everybody understand this example? Anybody have questions on this one? Okay, so questions? Anybody have questions on using the TI for normal CDF? I think some of you probably missed last time and you might have questions on that. Now let's think about the answer, okay? All right, so this means we'd expect about 1.5% chance that there are less than 170 defective heaters. Does that seem odd to you? What do you think about that result? Does it make sense? That's a pretty small probability. Why do you think it's so small? Anybody have any ideas based on the numbers you were given? I've referred to a few times that your mean is your expected value. Do you see what that value is? Okay. Your mean or your average is supposed to be 200 defects in a sample of 10,000. So it's reasonable that finding less than 170 isn't going to be too likely. Does that part make sense? Yeah. 2% of 10,000, right? That's 200 bad heaters, okay? So this makes sense that you'd have a very small probability of getting less than 170 defects in a sample of 10,000, okay? Does that make sense? Part of what I'm trying to do with my questions is I'm trying to get you to develop a certain amount of intuition about statistics, because it can really be a walk in the woods otherwise. Okay, you can really get lost unless you develop the intuition. Hey, that makes sense. That I was expecting a small number. I wouldn't expect a really large number. Okay. Yeah. Okay. We could actually do a binomial on this exactly and compare the answers. Okay, because again, I can run it with these numbers in an app. Okay, so you could see how far off you are with your approximation if you were interested in that. Okay, but I would rather move on to a second one. Okay, can you do this? Okay, same N and P values. Okay, let's see if you can figure out the probability of this one. Okay, more than 222 defects. Okay, try this one. You don't need to compute N and P again. You've got those. You just have to figure out what the probability is and what your adjusted X should be. Okay, again, I'll slide up to the table. Okay, so you're trying, okay, probability. I'll bring this up here so you can see it. Okay, Take it in steps. Remember, first you've got to adjust x, okay? We want to know more than 222, so that's x is greater than 222. That means I need to adjust it this way by saying x is greater than 222.5. Okay, let's just do a double check. What is your adjusted value? Okay, let's start in steps. What's your adjusted value for x? I want x is greater than 222. Okay, we have one vote for 222.5. How about the rest of you? If you were to put in x is greater than 222, do you see how you'd use the second line right here? 22.5. Good. Okay. Next question is, what are you typing into normal CDF? Okay, you can just type the command right into the chat box. Tell me what you're typing in. Remember, if you want to be greater than 222.5, that's the smallest value, right? Okay. You got to think at every step of the process, right? X is greater than 222.5 means you want all the values to the right of that. Okay, so 222.5 is your low bound. Try this one. Yes, absolutely. Okay, so try that one and evaluate it. See what you get for a value. Okay, putting that in our notes. Okay, so again, if I go over to my TI just to show you, okay, here's what I would do. Second, there's normal CDF. I'm going to clear out the stuff from last time that isn't relevant. Okay, so my lower bound is now 222.5. My upper bound has to be positive infinity now because I'm going all the way to the right, greater than 222.5. So that's 1 second, comma, 99. And leave the mean and standard deviation alone. And I get the same value the rest of you are getting. So again, that means there's about a 5% chance of finding more than 222 defects. Again, slightly larger than what you got before. Okay. Why is that? Well, 170 is 30 below your mean, whereas 222 is 22 above your mean. So a slightly larger chance. But again, still pretty far away from the mean. Everybody all right with these two? Anybody got questions about the wordings of the problem? Here's one last one for you to try. Okay. You try this one. Okay. And again, I'll kind of put some steps here. Identify N and P. Check assumptions for using approximation. Determine standard deviation. Just X. Find normal probability. Okay, so here's one last one. This will be the last one we try. Okay, try this one and follow the steps I've put on the screen. Try this. Okay. When you've got them, type your N and P values in the chat box. Let's do it step by step. Okay. What do you think your N and P values are? Remember, okay, that's NP, okay? We want N separate and then P. Okay, so how many trials, if you're doing a multiple choice test, what are the individual trials? That's your N value. Okay, what are your trials? It says the test has 120 multiple choice questions, and each has 5 alternatives. You are just going to randomly guess. You are not going to use your brain at all here. Okay, so yeah, your trials, you're right, Alejandro, your trials are the number of questions. So N equals 120. Okay, so I'm going to put that down here. Then, if N is 120, what's P? P is the probability of a success. How many outcomes are there for each question? 5. And we're assuming each question has a correct answer. So what is the probability of guessing the correct answer if you have 5 alternatives? Again, guys, we're assuming one correct answer out of 5 alternatives. Yeah, 1/5. Okay, so P is 1/5. I'm going to write it as a decimal. Okay, so 0.20. Everybody understand that? Anybody have any questions on that? Anybody have questions on how we got those? Okay. Next, check your assumptions. Okay, next, check your assumptions. Again, if you're stuck at any point, please just type a question in the box. I have to decide that n times p is greater than 5 and n times 1 minus p is greater than 5. Okay, so I have 20 times 2o. Four, which is greater than 5. That one's okay. And then I have 120 times 0.8. 96, which is greater than 5. If you want to see what I'm talking about by assumptions, you can take a look at what I have on the screen. Okay, the assumptions I'm checking are that n times p is greater than 5 and n times 1 minus p are greater than 5. Right? So if my n is 120 times 20.2, I get 24. That's greater than 5. Okay, and then 1 minus p would be 0.8. Okay, so 120 times 0.8 is 96. That's also greater than 5. So my assumptions are okay. Are you okay with that? All right, if you're stuck at any point, please chime in. Is it okay to move on? Are you all right with this so far? Next, I'm going to compute the mean, which is NP, which I've already got actually. My mean is 24. And then my standard deviation is the square root n minus p minus p. Yes. Good. Actually, your mu is the standard deviation. Okay, so mu is NP, which is 24. And yeah, sigma equals It's 4.38. Okay, everybody all right with this? Anybody questions about mu and sigma? How are we doing so far? Okay. Next step is to adjust your x value with the continuity correction factor. Okay. So again, I have my mu and my sigma. I'm going to just highlight those so you can see them. Originally, we wanted to get at least 32 correct. Okay, at least 32 means 32 or 33 or 34, all the way up to 120. So it's greater than or equal to 32. Okay. I need to adjust this using the continuity correction factor. So I'm going to look for greater than or equal in there. Okay, and if you see it's the last one, P is greater than or equal to N. So I'm going to use P as the probability of X being greater than or equal to N minus 0.5. Okay. So for X greater than or equal to 32, use okay, everybody see that in the continuity correction table? I'm using this last line. Okay, so this is going to be adjust. If I take half away from that, I get 31. How are we doing? Okay, questions at this point, guys? You're getting awfully quiet, so I'm assuming you're working ahead. Remember, I can't see you or see what you're working on, so you need to give me some feedback. So here's my adjusted X. And last but not least, I'm going to do a normal CDF. And again, since I want all of the X's that are greater than this, the 31.5 is my low bound. Infinity is my high bound. Mean is 24, and my standard deviation is 4. Okay, we've got some values. Okay, so type your probability. Type your probability in the box when you get it. Okay, we're getting a couple of same values, so 0. Again, I got the same probability value. Okay, so what does this mean? Okay, first of all, let's think about this. Okay, that value is about 4%. There is about a 4% chance of correctly guessing 32 or more questions correctly. Okay, just so you know, 32 out of 120 is about 26%. So what this says is you really have a really, really bad chance of getting a decent grade by guessing, okay? Because again, this is 32 or more questions out of 120, and you've only got a 4% chance of guessing them. So how about questions on this problem? Questions on this problem, are we okay? Everybody sure you understand where all the pieces came from? I'm going to stop sharing and go back to the meeting. I'm going to ask questions on anything. All right, are you sure you're able to find those continuity correction factors? They're in our My Math Lab course. They're in both the notes and they're in notes and videos, okay? All right, I'm going to stop recording then.